Let us continue our discussion with scalars, vectors and tensors. So, in the previous lecture we considered the elementary vector operations, the addition, and then we discussed the dot product. So, here we will continue with the second kind of product between two vectors, which is the cross product. So, if you take two vectors, so now we are going to make a object which has both magnitude and direction out of these two vectors. So, this is a vector out of two vectors, this is a cross product. So, again we take two vectors. So, A and this written in terms of the components Ax plus Ay plus Az, and B again as a component, and as before the without arrow represents the magnitude, and similarly for B, and similarly theta is the angle between A and B. So, then the rule that gives you the cross product is the following. So, this is denoted by the symbol cross or X between A and B. So, A cross B, and then you have a which looks a bit complicated looking rule, difficult to memorize. So, this is but this is not a random or haphazard. So, this is a particular specific combination of the components. So, Ay Bz minus Az By, that gives you the x component, Az Bx minus Ax Bz, that gives you the y component, and Ax By minus Ay Bx, that gives you the z component. Now, there is a simple way to remember this formula, which is, so to write down, so as this formula as a determinant. So, the first row you write down the unit vectors, second row you write down the components of the vector A. So, what is A? A is the first vector. As we shall discuss very soon, that the order in this product, the order in which you write the vectors going to be important. So, you have to keep track of the order. So, the vector that comes first goes to the second row, and the second vector goes in the last row. And then if you pretend that this is like a determinant of a matrix, and you apply the standard formula for determinant of matrix, you get back this particular formula. But remember, this is just a kind of a pretension, because in a matrix all elements of a matrix are numbers, whereas these are not just simple numbers, they are vectors, they are not scalar quantities. So, this is just a kind of a mathematical convenience, but this is not a determinant of any matrix. Now, there is a second way, just like in dot product we can define the dot product in terms of the magnitude and angle between vectors. The cross product is defined as the magnitude of B A, the magnitude of B, which is the second vector, now the sine of the angle between them, and then this represents the magnitude, and then there is a vector n which represents, so this is actually an unit vector n which represents the direction of A cross B. So, what is n? So, n means normal, which means perpendicular. So, n is a direction which is perpendicular to both A and B. To both A and B. Again, when we see this definition or some rule, some formula, so you have to ask again, does it make sense? And again, the first strategy that we learned is to draw sketches. So, let us say that this is my vector A and this is my vector B, and this is the angle between A and B. So, now again if I drop a perpendicular then what do I get? What do I get is that, so I drop a perpendicular from the tip of A to the on tip of B on A, then this represents the height, so of this triangle represents B sin theta. That means that if I complete this parallelogram by drawing parallel of the vector A and parallel of the vector B, then A times B sin theta represents the area of this parallelogram. So, in general it is a parallelogram. If A and B are perpendicular to each other, then this will be a rectangle, and you can. So, I will leave it as an exercise to you to verify this statement for this case when A and B are perpendicular to each other. Okay. So, this represents the area or the magnitude, and then so now you know that if I give you a two different arrows, then you can like two fingers, then you can so this defines a plane. So, this can be this plane, this can be this plane, this can be this plane, but if I give you two independent arrows, then they define a plane. So, the rule says that the direction of the cross product is perpendicular to both A and B, which if you think about it, it means that this direction of A hat is the cross product n hat is a direction which represents the direction which is perpendicular to the plane. So, this gives you the direction of n hat. Now, you have to, if you really try to do like take your finger or two pens or two pencils and try to sort of make sense that which is the direction, you can easily see that the direction is not unique. There are two directions possible. So, suppose this is A, this is B, then the direction which goes from upward and the direction which goes vertically downward. So, both are perpendicular to this plane. So, which of the, but a single vector cannot have two directions at the same time. So, in that sense, you just simply saying the direction is perpendicular to both A and B is little bit ambiguous. So, it turns out that we require a convention to select the direction of the cross product between A and B. So, the convention is that you apply a right hand thumb rule. So, if you go from, if you start from A, and so if this is your A and let us say this is your B, then you apply your right hand, not the left hand, right hand. So, you say start with right hand and then go to the, move your hand to the B, direction of B, then the direction of your thumb of the right hand gives you the direction of B, of the cross product A cross B. So, that means is a very interesting point that to define the direction of the cross product, you need to apply your right hand, and if you apply your left hand, you will get the wrong direction. So, that you need some convention to define this direction. So, the quantities for which you need this extra convention to define the vectors for which you need this extra convention to define the directions are kind of a special category of quantities, and these are called pseudovectors. So, we will not go into the difference between what the true vectors and pseudo vectors. We will simply mention examples that will be relevant for our course. So, these are the angular velocity, angular momentum, torque, etc. Now, again we try to unwrap the formula that we just introduced. So, namely this for cross product. So, let us say that we take some special case. So, let us say that we calculate the cross product between x hat. So, again we take our Cartesian component system. So, let us say this is our x axis, this is y axis and this is z axis. So, we want to know what is x hat cross x hat. Now, if I apply this definition, so a cross product of a vector, unit vector with itself. So, first I need the magnitude of first vector which is 1, magnitude of the second vector which is 1 and sine of the angle. So, the angle theta bit of a vector with itself is 0. So, sine of 0 which is 0. So, cross product of a vector with itself 0. So, this is different from what we seen from the dot product. Now, let us take two different unit vectors, let us say x hat and y hat. So, x hat cross y hat, what does it give? So, x hat cross y hat, so the magnitude is 1 times, so this is a null vector essentially. So, x, so this is 1 times magnitude of y hat is 1 and the sine, so the angle between x and y is 90 degree or pi by 2. So, this is sine pi by 2 which is 1. So, the magnitude is 1. Now, what about the direction? So, if you apply your right hand thumb rule, you go from start from x axis and move towards y axis, then your right hand thumb will point to the z direction. So, x, the cross product between x and y is the unit vector along z axis which is z hat. You can verify that if you take the cross product between y and z is x hat and the cross product between z and x is y hat. That is why the particular way I have drawn this coordinate system is called a right handed coordinate system. So, let us take an example to understand this definition. So, three vectors are given p, q and r. Find the component of p along q and a unit vector perpendicular to both q and r. So, let us do it one by one. So, the component of p along q. So, here you encounter a question. So, what kind of product we are talking about, dot product or cross product? And here you can easily feel that if you think in terms of, if you have a good picture of the product between two vectors clear in your head, then it is easier to attack this problem. So, remember the physical pictorial meaning. So, component of p along q, it represents the projection of p along q. So, we are talking about the dot product. So, we want to calculate the dot product between p and q. So, this will give me p times q times cos theta. So, the projection of p along q is p cos theta. Now, I want to go one step further and I want to define a vector which is in the same direction as q and whose magnitude gives you the component of p along q. So, the component of p along q will be p cos theta as we discussed before. Now, I want to draw a vector whose magnitude is p cos theta and whose direction is a unit vector along q. So, how to calculate this quantity? So, note that I can write this, now I apply the definition of dot product and unit vector. So, I can write this as p cos theta p times q times cos theta divided by q times q hat, which is same as q times p cos theta divided by q hat times the unit vector is the vector q divided by the magnitude of q. So, then I can combine them as saying that this is p dot q divided by q square times q. So, I am just this part gives you p dot q, these two combined together gives you q square and this q is this q. So, what is p dot q? So, we have to calculate these three pieces. So, what is p dot q? So, p dot q is, if I apply the component wise formula. So, I get 2 times 2 . So, there is no y component of p. The z components are minus 1 and 2 respectively. So, this gives me 2. Now, what is q square? So, the q square is 2 square plus minus 1 square plus 2 square. So, that gives you square root of 9, which is 3 square, which is 9. So, then our answer is 2 divided by 9 times the vector q. So, this represents the a vector whose magnitude is same as the projection of p along q and the direction is parallel to q. So, if you calculate the magnitude of this vector, that will give you this projection of p along q, the p cos theta. Okay. So, the next problem is to find the unit vector which is perpendicular to both q and r. So, this is straightforward application of the cross product. So, we need to calculate q cross r. So, let us apply this determinant formula q cross r. So, we write down in terms of determinant, which is easy to remember. So, q is 2 minus 1 2 and r is x component is 2, y component is minus 3, z component is 1 and this gives you x hat. So, minus 1 and then plus 6, which is 5 plus y hat times 4 minus 2, which is 2 plus z hat times, so 2 into minus 3 is minus 6 and then plus 2, which is minus 4. So, this is the vector which is q cross r. Now, I need to find out the magnitude of this vector q cross r, which is square root of 5 square plus 2 square plus minus 4 square, which gives me square root of 45. So, then the answer is, so this n hat which represents an unit vector which is perpendicular to both q and r is given by 5 by square root of 45 times x hat plus 2 by square root of 45 y hat plus minus 4 divided by square root of 45 z hat. Now, note that you can also define the vector minus n is also a unit vector, magnitude is same and it is also perpendicular to both q and r. So, the answer is plus minus n hat. So, two answers are possible. So, this is important. So, putting this plus minus is important. Now, I want to point out two crucial differences between dot and cross products. So, the first difference is that A dot B is equal to B dot A. If you apply the formula rule that defines the dot product, you can easily verify that. And now you apply the formula for the cross product and you will see that A cross B is not equal to B cross A. So, this is a crucial difference between a dot and a cross product. So, the cross product behaves like a real number, the usual multiplication 2 times 3 is 6, 3 times 2 is 6, 4 times 3 is 12, 3 times 4 is also 12. So, that is why it is called a scalar product. But the A cross B, the cross product is not a multiplication of two numbers, it is a multiplication of two vectors, and this is one place where this is getting reflected. So, A cross B is equal to minus of B cross A. So, you can easily see that. So, by applying your right hand thumb rule. So, if you go from A cross B, you are going from A to B and the direction is upward, whereas if you go from B to A, then you are going from B to A, then your direction is downward. So, the magnitude remains same, but the direction reverses. So, A cross B is not equal to B cross A. So, there is a, in that sense, that you have to take the direction into consideration. Next one is, as we explained or verified for the case of unit vectors, if you take the product, a dot product of a vector with itself, you get the magnitude square. So, A dot A is A square, yes, because when theta is 0, then cos theta is maximum, which is equal to 1, the magnitude of cos theta. Whereas, if you take the cross product of a vector with itself, you get the null vector or 0, because in the cross product what goes into the formula is the sine of the angle, and when theta is 0, the sin theta magnitude of sin theta is minimum, which is 0. So, this is another difference between a dot product and a cross product. So, do not get confused between these two products, pay attention to the notation clearly and remember that A dot A gives you a number, this is just a number, whereas the cross product gives you a vector which has both a magnitude and direction. So, I mean to be really technical, I should mention it as a pseudo vector, but for our purpose, unless under very special circumstances which we will not require for this course mostly. So, there is no difference between the vectors and the pseudo vectors. So, now in the I am going to cover two more products. So, these are called a product between when you have 3 vectors instead of 2. So, how can you combine 3 vectors, and so what will be the result? Will it be a number or scalar, or will it be a vector? So, let us take 3 vectors A, B and C. Now, you can see that if I want to make a dot product, I need 2 vectors. So, let us try to simplify 3 vectors to down to 2 vectors. So, how can I combine 2 vectors and make a vector? So, the answer, as you know now, is to make a cross product. So, let us say if I take these 2 vectors B and C, then B cross C is another vector. So, it is a vector, and then A is another vector. So, I can take now a dot product between this vector A and this vector B cross C. So, this is called A dot B cross C. So, this is a number because the final operation is a dot product, or a scalar, because we can easily show that if you do a coordinate transformation such as rotation, this number does not change from one frame to another frame, from the blue frame to the red frame. So, this is a scalar or a number. So, this is called a scalar triple product. So, since there are 3 vectors, so this is the product of 3 vectors. So, this is called a triple product, and this is a number or a scalar. So, this is called a scalar triple product. So, we can give a sort of a kind of simple geometrical meaning to this quantity. So, I am not going to prove it, I am just stating it. So, if you have this vector A and another, let us say this is your vector B and this is a vector C, then you know that so they together they define a plane, and in this plane if you complete the parallelogram, then the area of this parallelogram is B cross C, and then the B cross C is perpendicular. So, the direction is perpendicular following the right handed thumb rule. So, this is the direction of B cross C. Now, if you take another vector A, then the projection of this B cross C along A gives you the A dot B cross C, and one can show that these, if you have these 3 vectors, you can draw a 3 dimensional kind of a deformed cube which is called parallelepiped. So, this is, so if all of them are perpendicular to each other, then this will be like a block like a brick. So, this is like a distorted brick. So, this distorted brick, the volume of this distorted brick is given by A dot B cross C. So, this is something I am stating without proving, but this is a kind of an use or practical application of the scalar triple product. So, the next question is, can I make a vector out of 3 vectors? So, the answer is yes. How? Again you take these 3 vectors A, B and C. Now, if I take this pair, then I can make a cross product out of them, and then if I take a cross product of A, previous case I took a dot product between A and the cross product of B and C, but you can also take a cross product, and this is called a vector triple product, because the resultant is a vector, because this is a cross product. So, this is a double cross product. Now, I am going to, so how, so if I, so I am going to state an identity. So, which says that A cross B cross C is equal to B times A dot C. So, A dot C is a number, is a scalar, minus C times A dot B. So, this is usually known as, so this is BAC minus CAB, hence it is usually known as back minus cap rule. This is a kind of a useful mnemonic or help you to remember the formula. Now, this is an important point, which is that suppose I just write 2 vectors, 2 cross products like this. Now, which order I take the cross product, is it important? That is, if I take the second cross product first and then the first, versus if I take the first cross product first and then take the second, at the same, let us check that. So, if I apply this back minus cap rule, so then this basically gives me the formula, the rule basically says take the middle vector. So, write the middle vector first and then take the dot product of the remaining 2 vector, and then take the last vector and then take the dot product of the remaining 2 vector. So, now if I want to apply it here, first I have to write it in this particular form. So, A cross B cross C is equal to minus of C cross A cross B. So, you have to write it in this particular form. Then the middle vector becomes A. So, then take the middle vector out and then take the dot product of the remaining two vector, which is C dot B, and then minus the last vector, which is in this case B, and then take the dot product of the remaining two vector, which is C dot A. And note that there is an overall minus sign here. So, then it becomes B times C dot A minus A times C dot B. Now, as I discussed before, this C dot A is equal to A dot C. So, now if I compare this expression with the previous expression, when I take the second vector, then I get one term same, but the second term, this term are different. So, that means these two are not same. That means, if you have two cross products one after another, you must always give a bracket to denote which cross product is taken first and which cross product is taken next. The order is important. So, the order is of cross product is crucial. Okay. So, this sort of concludes the our very basic and quick review through examples of the basic math, the scalars and vectors that is required for this course, which is on the Newtonian mechanics through examples. So, in the next week we shall start with the physics or review of the Newtonian mechanics. So, we shall see you again next week. Thank you.